The ultimate goal of Industry 4.0 is to engineer cyber-physical systems. Physical processes and digital models co-evolve in real time, meaning the digital replica must mirror exactly what the physical machine is doing the moment it happens. Physical manufacturing operates on absolute certainty. If an actuator needs to trigger, the machine control requires a zero margin for error deterministic loop. It executes on a strict millisecond schedule. Deep learning and artificial intelligence are the exact opposite. They are inherently probabilistic, relying on massive, complex computations to find patterns in high-dimensional data. This creates a central engineering paradox. You cannot wire a computationally heavy, latency-inducing neural network directly into a safety-critical physical machine. If a robotic arm relies on an AI to issue a millisecond perfect halt command, and the AI takes a second to process, the machine crashes.
Legacy approaches try to bypass this by sending all raw sensor telemetry straight to a centralized cloud for analysis. But routing data to a distant server and waiting for a response fails to meet the sub-100 millisecond response times required for factory floor actuation. Physics does not wait for network lag. The structural solution is to architect a multi-layered cyber-physical system. We have to physically and logically decouple the safety-critical control mechanisms from the higher-level adaptive analytics. True digital transformation is not a software add-on. It requires a spatial and logical co-design of exactly where and how intelligence is deployed across the facility. Most industrial deployments are brownfield. Architects cannot build from scratch. They have to retrofit legacy machinery to extract data without compromising operational safety. This closed-loop schematic maps the foundation. A physical sensor feeds data to a PLC, which dictates actuator movement. This loop operates on strict millisecond timing and absolutely cannot be interrupted. But to run analytics, we need to extract telemetry without breaking determinism. We need an intermediary step. A hybrid PLC, SCADA, IIoT pattern acts as a one-way mirror, letting telemetry out without letting IT network traffic back in. We format this extracted data using OPC UA for interoperability. An MQTT broker then routes these structured tags outward via deterministic Ethernet, guaranteed by time-sensitive networking. Establishing this deterministic base ensures the physical machinery remains perfectly safe, while simultaneously opening a secure telemetry pipeline for the analytics layers above. The data flowing out of these machines is multimodal, comprising vibration, temperature, current, and event logs, arriving at high volume and high velocity. The immediate architectural challenge is deciding the physical location where this massive telemetry stream should be processed. Cloud platforms traditionally handle this workload. They provide scalable storage, long-horizon analytics, and the centralized compute power needed to train cross-facility machine learning models. This flowchart illustrates the flaw of relying entirely on the cloud for real-time operations. Sending data to a distant server creates round-trip latency and leaves the system vulnerable to network dropouts. To solve this, we introduce the edge computing layer, lightweight nodes placed adjacent to the PLCs. Executing machine learning inference close to the source guarantees the sub-100 millisecond response times required for closed-loop optimization. The edge also provides resilience. During intermittent disconnects from the broader IT system, the node uses local buffering to safely maintain the machine's control loop without dropping telemetry. This creates a strictly hierarchical deployment pattern. Raw sensors feed edge pre-processing, which handles local inference, then passes aggregated results to the cloud. In a cyber-physical system, the spatial placement of computing power is a mandatory physical engineering requirement, not merely a software deployment preference. Looking at the internal logic running inside the edge node, the objective is to translate raw industrial data into predictive intelligence. This requires robust feature engineering. We combine domain-informed statistical transformations with physics-aware features to filter out heavy industrial noise and isolate the true signals. In predictive maintenance, the primary target metric we extract from these signals is the machine's remaining useful life, or RUL. This graphic shows the sequence modeling required to estimate that lifespan accurately, relying on deep architectures like a convolutional neural network paired with long short-term memory, or CNN-LSTM. The contradiction here is that CNN LSTMs are heavily demanding on compute resources, but our shop floor edge devices are highly constrained by both memory and power. We resolve this through model quantization. By reducing bit widths and pruning neural nodes, we compress the deep architecture to execute efficiently on edge hardware, while entirely preserving the RUL estimation accuracy. But local edge inference has a severe limitation. An isolated machine cannot learn from the failure patterns of similar machines in other global facilities. We solve this with federated learning architectures. The edge devices aggregate and send only their mathematical model updates to the cloud. The global models improve, but the proprietary raw telemetry never leaves the localized factory floor. Industrial AI requires squeezing advanced predictive logic into the smallest possible footprint, while ensuring multi-site learning remains collaborative and strictly private. Moving outward from the autonomous network, we reach the human-operator interface. A cyber-physical system is only as effective as its human-machine integration. Deploying opaque, black box AI models in an environment where physical safety and asset integrity are at stake is a severe operational risk. Operators must know exactly why an alert is triggering. This dashboard illustrates how we integrate explainability frameworks, such as SHAP and LIME, directly into the operator interface. These frameworks unpack the model's logic into traceable decision paths, showing exactly how variables like temperature and vibration contributed to the alert, building immediate operator trust. Mechanically, the dashboard must provide a safe override. This interface connects directly back to the hard-coded PLC safety guards, instantly superseding any AI recommendation if the operator detects an issue. This entire human-machine interaction operates within the strict perimeter of IEC 62443 security governance, ensuring cyber attacks cannot manipulate telemetry or alter the machine learning models. To maintain this perimeter, engineering teams rely on operational practices like DevSecOps and MLOps to continuously deliver and govern these secure, reproducible software pipelines. Human trust, mathematically explainable logic, and unyielding physical safety overrides act as the ultimate limiters and enablers of advanced automated control. Pulling back, we can view the sum of the architectural components, from the foundational machine loop, bridging upward through publish-subscribe protocols, into the quantized edge, and finally to the federated cloud and explainable operator dashboards. This fully integrated, synchronized stack is the canonical instantiation of a cyber-physical system, the digital twin. The ISO 23247 standard provides the formal, industry-recognized framing for deploying these exact architectures across manufacturing environments. The core thesis remains constant. Long-term success requires separating the high-speed deterministic control loops from the adaptive analytics loops. We bridge them seamlessly via structured telemetry protocols and highly localized edge processing. This meticulously co-designed architecture proves why the naive approach of simply migrating raw factory data to a centralized cloud will always fail the demands of real-time control. By mastering this spatial and logical topology, architects move far beyond isolated factory automation. They engineer true, resilient intelligence into the physical world.